Hello, my name is Andres Littner, and my final project is around using reinforcement learning in custom made environments that should be created to solve real world problems or be similar in spirit to real world problems and make reinforcement learning algorithms to solve them. So basically, the goal is to, instead of using existing environments such as the gym from OpenAI, to create my own environments and solve them and see how the different algorithms work. So some of the environments will be extremely simple and the optimal strategy for them will be trivial, but for others maybe there will be more complex behaviors and more complex trade-offs that will like the agent to assess, and hopefully we can learn from them, from the solution they get to, and hopefully we will have some insights around that and maybe we can learn something from it. So the the idea is to solve these environments through the use of deep Q learning algorithms, and I did my solution in Python, so I'm going to make use of three main packages. It's mainly NumPy, Random, and Keras. And the steps of this project goes as follows. So the first step is to create two simple environments that will serve for training for our agent. Then to train our agent in those environments by using a deep Q learning algorithm. And finally is to report and assess the quality of the results. So I created two main environments, one which is very simple and the other one it's a bit more complex, so I'll go over them in a moment. So these two environments are mostly games in a way that you play against a computer, and the idea is to get as high a score as possible. So let's go over the first environment. The first environment is a game which is extremely simple. It goes like this: the computer chooses a number from 1 to 5, and then the agent or the player chooses a number from 1 to 5, and the rewards or the scoring goes as follows. If the computer chooses 1 or 2 and the agent chooses 1 or 2, it will get a score of -10. If it chooses 3, it will get a score of 0, and if it chooses 4 or 5, it will get a score of +10. If the computer chooses 3, on the other hand, then if you choose 1, 2, 5, or 4 or 5, you will get a score of -10, and if you select 3, you will get a score of +30. And finally, if the computer chooses 4 or 5, then if you or the agent chooses 1 or 2, you will get a score of +10. If you choose 3, a score of 0, and if you choose 4 or 5, a score of -10. So this is basically the first environment. So the optimal strategy here is super simple. Before we go over the optimal strategy, the total game is played 200 cycles. So each game is comprised of 200 of these kind of interactions. And as we can see here, the optimal strategy is to play when the computer plays 1, play 4 or 5, 2 the same, 3, 3, 4, 1 or 2, and 5, 1 or 2. This is how we get the maximum possible score. So it is always instructive to think about some benchmarks for the results of the game. So one of the benchmarks we can think about is random play. So how many points we will get on average or an expectation if we play randomly, and we can see that on average we will get -80%, -80 points each game if we play totally randomly. And if we play the optimal strategy, we will get at most 2,800 points for each game. Again, each game is comprised of 200 sort of stages or cycles, as I call them. So let's go over the environment number 2, which is slightly more complicated and I would say a bit more interesting. So in this game, I wanted to sort of include some kind of medium or long-term considerations for the agent. Because in the first environment, if you noticed, the score is only affected by the decision you take at each point. There's no longer term effects of your decision. So here in this second environment, it will be slightly different. So the game goes like this. The computer starts always by choosing a number from 1 to 100. It starts always by choosing 50, okay? And then the agent has to reply with a number again from 1 to 100, and the scoring system goes as follows. If the agent chooses a number lower than the computer's, it gets minus 20 points. If it chooses the same number as the computer, it gets 0 points. And if it chooses a higher number, then the score is as follows. If the difference from the number chosen and the number the computer chose is higher, you'll get a higher score as according to this table, okay? And then for the next cycle, basically the computer always chooses a number 2 numbers higher than the number chose by the agent, okay? So this is mainly the environment number 2. So for example, if the agent played 45 in the previous cycle, the computer will play 47 in the next cycle. In this sense, the game is kind of, or the computer reaction is sort of predictable in that sense. Okay, so this is a very interesting setting in the sense that the computer at some point will get to 100 if the agent plays reasonably well, we would say, and then at that point the agent will be presented with an interesting dilemma, okay, because it will be able to choose 100 and get 0 points in that step, but on the other hand it may decide to pay minus 20 in that particular game, so just a lower number from 100, with the hope of recovering this from this negative score in future steps by selecting higher numbers in future steps, future cycles. So that's kind of the dilemma here, and sort of the more strategic behavior that it's sort of required, or strategic or medium-term, long-term understanding that is required for the agent to succeed in this game. So let's go over the benchmarks. Here we have an optimal, first of all, let's start with random play. And I have to say, this is a game that even for me, it's quite difficult to think about in terms of calculating exactly what's the number for random play. So I just did a simulation, okay, 3,000 games, and again, each game is comprised of 200 cycles. And I calculated the mean of this score and the standard deviation. So it's around, actually this is the exact number, it's minus 976.8 with a standard deviation of a bit more than 100. So let's say roughly it's minus 1,000 points per game if you play randomly, okay? And then the optimal strategy, I have to say again, it's not so easy for me to calculate the optimal strategy. We can sort of think about it and try to see what would be exactly the total best strategy to go here. But I can say, just to make things easy, I would say a fairly good strategy would be to choose 100 and then 1 and then 100 and so on and so forth, and we will be getting 250 points in an entire game. Okay, so we'll have this sort of calculation: 100 times 2.5. Okay, that will be the sort of the entire score, which is, as you can see, much better than minus 1,000. That it's the benchmark for random play. So again, I'm not entirely sure this is the absolute best strategy, but it's a good approximation, and it's good to have it as benchmark, and it's a good approximation of the optimal strategy. Okay, so now that you have the environments, we were going to train the agent on these two environments and see how, with a deep Q learning algorithm, and see how it works, okay, and see the results for them. So let's visualize a bit, or show the visualization for the training results for the environment number one. We see actually that the agent seems to learn how to play and improves relatively a lot in 1,000 episodes. Each episode is comprised of the whole game, okay, 200 cycles. So it manages to go from 0, which would be the random play in this case, to a sort of plateau of sort of 1,800, which is pretty impressive, okay. It is still far from the total optimum, which will be, as we said before, 2,800, but it does a pretty good job, I would say. Right, so this is environment number one. Environment number two, we have the same thing. We start with around minus 1,000, which is the random play, and then we sort of approximate asymptotically to around 0, I would say, and we get to a sort of a plateau. So I would say it's kind of difficult to get to higher levels at this point in this training. And again, here I would have to say it's very important, something I didn't mention before. It's the discount rate I used. In the environment number one, I used the discount rate of 100%, because I sort of understood that all the actions only impacted the same cycle and did not have an impact on further actions. So I said, okay, let's use a discount rate of 100%. Further scores are really not related to the action the agent takes at each point. And for environment number two, I tried to convey the importance of this sort of strategic play and say, okay, there are some discount, but actually future scores are actually related to the current decision. Okay, so it's not just affecting the current score, but also each decision also affects or might affect scores in the future. So let's go over the results for environment number one. We see that mostly the agent managed. This is sort of a simulation after 100 episodes of training. So we see here in the first number of these tuples is the number the computer played, the number that the agent played, and then the score. So we can see this is sort of a snippet, but it goes on for the entire simulation, and it seems like the agent managed to get the optimal strategy. Okay, so let's sort of summarize it here. When the computer plays 1, the agent plays 5 and gets a reward of 10. When the computer plays 2, also the agent chooses 5 and gets a reward of 10. 3 and gets a reward of 30. When the computer plays 4, the agent plays 2 and the reward is 10, and 1 is 10. Okay, so there are a couple of instances, and I'm not showing this here to not make the presentation very long, which the player plays randomly, because still we have an exploration parameter which converges. The minimum value it can get is 1%. So 1 out of 100 times it will play, on average it will play randomly. So this is the time, but besides from that it plays optimally. And for environment number 2, these are the first 40 mini games for environment number 2 after almost 300 episodes of training, 3,000 games. So let's see what it does. Okay, so when the computer chooses 50, the agent chooses 100, which is pretty good behavior. Then when the computer chooses 100, again as a result of what the agent chose, the agent chooses 66, which is clearly not a good idea. Of course you will get, in any case, you choose a lower number, minus 20, but you should choose as lower a number as possible. Then and then here we see a kind of interesting behavior. Again, from 68, it chooses 100, which is pretty decent reaction. It's not the best thing it could do, but it's still good. And then a kind of loop from 100 to 100. Okay, so it gets reward 0, and after a couple of times of doing that, then the agent chooses 5, very low number, which is pretty good, and then a very high number after that. So, and then a lot of times which the agent chooses to play 0. Okay, so kind of interesting behavior. The agent manages to grasp some kind of strategy here, and it's quite interesting. It's not yet the absolute best strategy, and we can think, for example, as I said here, the agent seems to make a couple of errors, and we can easily devise some kind of better strategy for a couple of these actions. Okay, but it's pretty decent behavior. So this is all the explanation on that. So it doesn't play perfectly yet, but it has made considerable improvement from the very first stages, where it didn't know anything about the game. But then at some point, I have to say, I realized something, which is that for the second environment, I used maybe too high of a discount rate. Okay, so sort of I understood why it may decided to play 100 after 100 and choose 0 over getting minus 20 and then maybe getting even higher results, and say, okay, let's make a slight modification and say, okay, instead of getting 25, if you choose a very high number, in this case, in the original environment, this was 25, and I changed it to 100 to make it univocally a good strategy to go to very high numbers. So sort of to make sure that it will be convenient for the algorithm to pay this price of minus 20, because then at the next stage it could get ideally 100. Even if I discount it by 70%, sort of using a gamma of 0.3, I still would get, if only I looked at these two stages cycles, I would get 10 points, which is better than 0. Okay, so I wanted to test that, and here I run this training again, and this is the result I got. Okay, so when the computer played 50, the agent played 100, which is the best action it could take, and then it all the time sort of gets to a loop where the agent chooses 4 and then 98, which is great. It's getting minus 20, then 100, minus 20, 100, and so on and so forth, and we can really see that the agent picks up the optimal strategy. So in conclusion, this was very interesting for me to see. Ideally, this playing with or constructing in advance these kind of environments, it was like, for me, very simple way to show how we could sort of put in an environment all the sort of trade-offs or all the intricacies of we can build kind of a very complex game, and the idea maybe is to try to mimic some kind of puzzling behavior we see, or sort of try to put in a game all the trade-offs that we see in the real world sometimes for some particular situations, and make or try to make or making the agent solve it and see if we can learn something from it. Okay, in this case, even the second environment was easy enough for us to devise some kind of optimal behavior, at least for the very simple case. But we can push this to the limit and see if we can make the agent do something that would even surprise us in terms of the strategy of the agent. Okay, so also one learning from all this process for me was the importance of hyperparameters. Okay, I document this more in my report. is that the discount rate is very critical for the success even of the learning. Depending on the discount rate, sometimes the the agent may even not learn at all, or maybe sort of get significantly worse results depending on the discount rate you use. It was very puzzling for me. I documented that in the report, so you can watch it there. And also, okay, of course, you have other hyperparameters you sort of need to tweak, sort of just like the learning rate and the decay of the exploration parameter. So it was not so easy to get to this to get right, to get these parameters right. So this is something I also wanted to mention. And ideas for future work, I would really like to continue this project, and I'm going to do that eventually. And one of the things that it would be interesting to see is, or to add, is a bit of stochasticity in the play of the computer. In my game, it was very easy. It was just doing whatever the agent did plus 2. But then we could also increase some sort of stochasticity there and say, okay, maybe the computer can play with a distribution of values depending on the value of the player. So this could make, of course, the game much more complicated and difficult. But it could be interesting to see how the agent manages to learn the appropriate behavior, how to manages to solve or to navigate all this sort of uncertainty. And another very interesting possible extension of this work is to try to make the computer also play strategically, sort of in that sense, two players playing one against each other, and the idea is for each one of them to try to get the highest score as possible. Okay, so this reminds me of AlphaZero project, where which is a reinforcement learning engine, which eventually learned to play a couple of games such as Go, chess, and shogi, mainly by self-play. So we could eventually make this sort of game, or this algorithm play against itself and learn from it, instead of just sort of making one of the parts do a very simple behavior, just as I explained before. So I hope you like it, and this is the main work about this. Thank you.